Um, Professor Mulholland, thank you very much for a very generous introduction. Colleagues, ladies and gentlemen, friends and family, some who've traveled a long way, and I appreciate very much what they did. I'd like to start by saying, well, my title here, To Engineer is Humane, is a reference to trying to figure out why I've been doing this work for the last 20 years. What I'd like to do during the presentation is establish my motivation, and I'd like to do that by considering some useful biological systems and then to focus on bioelectrochemical systems in particular. I'll then sum up and hopefully we can all go and have a nice meal or at least something to eat. So establishing the motivation first of all, I'd like to thank a lot of people for helping me get this presentation together. It's not a one-man show. So I'll point to the things they've done where I can on the way through. Let me start with this. When I was a teenager, I think the biggest worry we had was the fact that we were worried about a nuclear holocaust. Actually, that worry seems to have gone away, and what seems to have followed it was an absolute deluge of information and chronic situation which has developed in our environment. And it's become a large problem for us. What will happen to our environment? What will happen to us because of it? And I think that raises a risk, and that risk is that we basically lose interest. So we may get to the point that we say, "What me? Worry?" Which is Alfred E. Newman from Mad Magazine, going back to 1956, year of my birth as it happens. And we may end up in the situation where we're hanging over the precipice by our teeth for want of releasing our hold on fossil fuels. So let's look at some definitions for the key words in the title. The first one being engineer, but engineering is what's implied. The bit that appeals to me is the last one there, which is calculated manipulation or direction as of behavior. And this is intended primarily for social sciences, but I think it has much wider implications, and I think it suits the way I think of engineering quite well. The second key word is humane, and my favored definition there is marked by compassion, sympathy, or consideration of humans or animals. So the title of my presentation tonight is a nod and a wink to a seminal work which was published early part of the 80s by Professor Henry Petroski, which was entitled To Engineer is Human as opposed to Humane. So the thesis that Petroski put forward was essentially that design and engineering development progresses on the basis of a whole lot of disasters that are almost inevitable because we tend to push into the areas of science and engineering that we know least about. And he listed a series of examples, like for one of them is the de Havilland Comet, which was an aircraft that suffered fatigue in the 1950s, and several people were killed in serious accidents. And another was the Tacoma Narrows Bridge. And that set me to thinking that perhaps what we are doing is taking our planet and doing something similar. Are we designing our way towards a disaster in the planet? After all, the world is just another system, no different from an aircraft, essentially, or from a bridge. and we run the risk of going beyond our knowledge and causing such a disaster. And I was thinking, is there any analogous systems? What I wanted to do, though, was show you the bridge in case some of you haven't seen it previously. So you can see the bridge go into oscillation. The wind, the crosswind, was generating vortices, which were exciting the bridge to the point where it broke down.
The suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
I don't think the dog felt very fortunate. But anyway. So this the slide that you see here was taken about 2 weeks ago. It's the Haiyan typhoon as it was approaching the Philippines. I don't think I need to show you any images of human suffering or damage to their property and so on. You've probably seen enough of that, but about 3,600 people were killed in that disaster. And it was the 25th typhoon to hit the Philippines this year. And of course there's been many others. We could list them, but I won't bother. So we might ask ourselves, is the weather actually linked to human activities, particularly to our emission of carbon? So the International Panel on Climate Change, very recently, at the end of last month, published a report on climate change, which was aimed towards policymakers, and I commend it to you. It's a very measured report. It quantifies uncertainties, and it also quantifies the confidence limits on the conclusions they make. And what's more, it says a lot of things. And for example, since industrialization, we've got 40% more CO2 in our atmosphere, and of the CO2 that's been emitted, 30% has been taken up by the ocean, and that ocean is now becoming acidified, and we're expecting to lose 30% of the species in the ocean. I think that's rather dramatic myself. And I quote, "It is extremely likely that human influence has been the dominant cause of observed global warming since the mid-20th century." And I think that's good enough for me. So let's move on to population, and particularly population growth. And we're in an exponential phase, and these are the projections of the UN population statistics. Remember that the world's a closed system, and we all understand money, and at 2%, our £100 will grow. It'll take 35 years to double, but in the next 35 years it'll double again, and so on. At 10%, of course, it's quicker, but nevertheless it doubles in the 7 years, and it keeps on doubling. So it's accelerating, in other words. So if you have a closed system, can we possibly believe that our population can keep on increasing? I would suggest it can't. It's not even desirable, I would say. So the projections from the UN are between 6 and 16 billion people on the planet, and all other projections, like from Deutsche Bank, etc., are within that range. Our growth rate in the UK is about 0.5%, a little more, and the world overall is about 1%. And there's a glimmer of hope in that our population growth in many countries in the planet, if you look at 13-year-olds and the numbers of 13-year-olds, which is an indication of population growth, they're tending to decrease in a lot of countries. Let's look at an analogous process, one that we can do on a desktop, but is effectively a closed process, a bit like the world. The world's not entirely closed, and nor is this particular process entirely closed. But what it does, it takes bacteria, and the bacteria consume their food, and they produce a gas, and the gas is a mixture of CO2 and hydrogen. So it represents metabolism, it represents life. So if we put a fixed amount of food into this reactor, what happens? is that the food runs out. And when it does run out, you can see that we have a curtailment of that activity and eventually a cessation of life. So another seminal work, and this particular work was published by Meadows and co-authors, and it was called The Limits of Growth. It was published in 1972, first one, and the copy I have is 1974. But the important issue is that they produced a world model, as it were, and what they looked at was resources, food per capita, population, industrial output per capita, and pollution. And if you look at their model, you can see the red dotted line. You have a reduction in the resources available as they're consumed, and you see an increase in population and just about everything else coming to a hiatus before collapsing afterwards because of lack of resources. So what happens if suddenly we have access to more resources? Perhaps the technologies improve. All that does is move that hiatus further along in time. So it happens a bit later, but it still happens. At the time that they did this work, they found actually they could do a scenario where you didn't collapse after the hiatus, that you had sustainable living after the rise. Unfortunately, what the world's done since they did this work is pretty much followed their standard model, which is what you see on the screen at the moment. So if they're right, what we're heading for is a hiatus followed by a collapse. If we look at food, and specifically the price of food, and associated to unrest for any cause. This is what Lagi and his co-authors did as well. Just plotting the food prices, the UN food prices, against riots in various countries. And he came up with an extraordinary correlation between the two. And you can see places like Mozambique, Yemen, and so on had riots in about 2008. And 2011, again, there was a whole lot. The predictions didn't work so well because what we've been calling the Arab Spring has developed into civil war in several places. So if we imagine that we're going to go from 7 billion to 9 billion people, it's not an unlikely scenario, it's going to take about 19% more water to grow the food to feed these people. And already we're using about 70% of our water on agriculture. And it takes a lot of water to grow food. So if you take, for example, 150 gram steak, it takes about 2,000 liters to produce it. A slice of bread takes 40 liters to produce it. So water is really a food issue as well. If we look at energy, we have reserves. This is a comparison of the quantity of energy in our reserves, uranium and oil, gas and so on. And also the irradiation for 1 year from the sun is the blue vessel there, if you like. We look at our consumption over a year, 2001, it's a little red cylinder at the top of the blue one there. And in 2050, that's in 2001, so 2050 is the little purple one next to it, so it's increasing. But our reserves are fixed. The total biomass we produce is down the bottom corner. That's on the planet, the biomass growth. So it's quite a small quantity in comparison to how much we use in terms of energy. One thing's for sure, that our reserves are fixed, whether we've calculated them correctly or not. And at the moment, there's an expectation that peak oil will happen in about 5 years. That may change because of fracking, but nevertheless, we just move in the time domain a little. Water and sanitation is another horror story. We've got about 3.5 million deaths per year estimated because of poor sanitation and water supply. And most, that's 80% of the world, has no sewage system. We have something like 36 times the population of this country with no sanitation whatsoever. 1.8 billion don't have a toilet. So you can look at where the water comes from, all the catchments, the aquifers. A lot of them are dissected or split by boundaries, by national boundaries. And that's a recipe for conflict. Although we should say that a lot of international agreements have been made, and hopefully they will continue to be made. So water scarcity is important, and the use of water is rising at twice the rate of the population. And there's an expectation that in developing countries there'll be an increase of 50% of water extraction by 2025. So by 2025 we expect to have about 1.8 billion people described as having absolute water scarcity. So this is thirst. And 66% of the planet under stress conditions. So I don't think I need to convince you that water stress can lead to conflict. Actually, because somebody else has done it for me, and it was published in 1993. Glick looked at this, and I quote from that paper: water already contributes to conflict among nations, and the future conflicts over water are increasingly likely. So what do we have in prospect? We have this increase in population and activity and everybody doing wonderful things, and then suddenly we reach a hiatus and we collapse. And the collapse isn't going to be comfortable. It's going to be worse than depressions that we've seen and recessions that we've seen. So there's going to be a recalculation of what the population, or what population can be supported. So what can we do about it? It looks inevitable to me. I don't think there's anything that democratic countries, or indeed the Chinese by the look of things, can do about it. We can't restrict population growth by unnatural means. So we need to engineer our way out of it. We need to try and make the landing, the collapse, as soft as possible. So this is justifying what I've been doing for the last 20 years, the research I've been doing. So it's that soft landing and the engineering associated I'm talking about now. So I'm focusing on bioprocesses, and I've worked on several other processes, and I hope anybody here who I don't include in this discussion can forgive me for that, but the time just doesn't allow it. So this is a rather complicated diagram, and I couldn't possibly expect you to assimilate it in a short period of time. It's not comprehensive in any case. It's bioprocessing, so what I'll ask you to do is imagine that you are the bioprocess. Okay, and we'll look at each of the columns under the blue heading there, and we'll see what it means as though we are the bioprocess. Okay, so the first one is feedstock, which is basically food. We've got to get our food, it's farmed and so on. We need to go to the supermarket and what have you. The second one is the pre-treatment. That's cooking and chopping and chewing, and even coming down to the enzymes in your mouth and your saliva, starting the digestion process. And the bioprocessing, well, that's effectively our digestive system, and it's extracting energy from our food, and usually it's storing it somewhere, usually where we don't want it. We then have post-processing, and there's a lot of things that can happen to the energy in whatever form it's coming out. It may come out as materials, but for us it's running and jumping and making things and making cars and making children and excreting and all the rest of it. So this research unit, research center that I belong to, was started off in anaerobic digestion, and I'm very glad to see Dennis and Frida Hawks here, who set it up initially and expanded. Actually, fermentation is part of anaerobic digestion, and the area is expanded to cover this whole area, the whole slide, as it were. And that includes bioelectrochemical systems. But I have to necessarily restrict myself to the red square there for this evening. So anaerobic digestion is the starting point for the technical discussion, as I might say. So it's convenient for us to have some sort of model in our head as what's going on in there. So we would have some sort of feed which is supplied to a reactor, and that's generally a complex feed. You can see it up at the top there as a composite. It's then broken down by all sorts of physical and chemical attrition and hydrolysis into simpler molecules which are accessible by bacteria. So these bacteria are very plentiful, and they are really the business. They're the catalyst that convert it to anything we want. And the things that they convert it to are volatile acids, things that smell like vinegar and smelly socks and cheese and so on, but actually very valuable chemicals. We can also produce hydrogen in there, and from the volatile acids we can produce methane as well. There's other processes happening, going sideways now, the generation of gases which are separated simply by the physical properties. There's dissociation of acids into the ionic form. There's partial pressures happening above and below the liquid line. So we have a lot of processes going on and a lot of different populations of bacteria doing it. So this is it gets more interesting, I think. Professor Lettinger some time ago discovered that these bacteria agglomerate together in the right conditions, and that allows us to retain them in a reactor and so make the whole process a lot more efficient. And on the left-hand side you can see one of those granules made out of bacteria evolving gas, and the gas causes its buoyancy to change and causes it to circulate within the reactor, giving it access to its food. On the right-hand side you can see the marbling effect within the granule, which is self-organizing bacterial species, so that what's being digested by one and producing products, the products of one species is the food for the next. You can imagine these to be a bit like a blue bottle or a Portuguese man of war, which looks like one creature, but actually isn't. It's made up of a number of different creatures which behave as though they are one creature. So we've looked at what the biomass, the materials, the food for these bacteria could be, and we looked at it specifically in the UK for production of methane. And we saw that we could produce, on the bottom line, forgive me, I don't have a pointer, about 1,000 petajoules, and that's 10 to the 15 joules. A joule's like picking up an apple 1 meter. It's the energy that it takes to do that. So it's more or less the number of stars in our Milky Way worth of apples being picked up a meter. So it's a lot of energy. However, it takes energy to produce that energy, so we end up with about 60% of it. It's equivalent to about 15 million tons of oil. That's probably quite optimistic. We would be using just about everything we had in the country in a bioprocess. But nevertheless, a good proportion of that could be available. So I've worked in looking at trying to improve the anaerobic process by splitting it into separate processes, and particularly in generating hydrogen from the first stage of that as an extra energy gas. These are three systems at pilot scale, and their corresponding funding bodies, and you can also see actually Jamie Massanet-Nicolau, who's now a faculty, and basically that process was his baby. I'd like to focus on bioelectrochemical systems now, if I might, and look at these bioelectrochemical systems, BES as they're called, for their opportunities and indeed their problems. Without their problems, we wouldn't have a research. So, biological oxygen demand is both energy and pollution, both at the same time. If it's in a river, it'll kill the fish. If we can convert it into electricity, that would be nice. So about 2% of the UK's electricity is used in treating our wastewaters. And it's pretty much the same elsewhere in the world. And 55% of that energy, of that electricity, goes into simply putting oxygen into the water that aerobic bacteria are living in, eating the BOD. So if we can avoid that, we can save enormous amounts of energy. We estimate that across Europe, in total, about 13 terawatt hours of energy. So bioelectrochemical systems then. Over the last 12 years or so, these devices, their power output, particularly thinking about microbial fuel cells, in other words, the electrical power output, has increased exponentially. So these are laboratory devices, but we know about exponential growth. And we're up to about 2.5 kilowatts per cubic meter, and we haven't seen the end yet. So that's quite a high power density. So what's the holdup? Why aren't we just deploying these systems and turning all our wastewater, all our sewage into electricity and cleaning it up at the same time? Well, the reason is, as soon as we try and make them bigger, we lose all the energy. The internal losses become so great that the efficiency of the process drops off drastically. But getting to large scale is absolutely necessary if we're going to make any use of them. So what I'd like to do is just explain how they work. First of all, the microbial fuel cell, which, as I said, is a subset of bioelectrochemical systems. We have an anode, which is the messy bit on the left, covered in bacteria. And on the right, we have a cathode, and it's separated by a membrane, a proton exchange membrane. So we could feed it something like sugar, and that sugar is hydrolyzed and made available to the bacteria who consume it. And these particular bacteria are capable of transferring electrons directly to solid surfaces. That's their function in nature, or that's how they get their energy in nature. So we then have electrons that we can pass through an external circuit. The protons that they also generate can go through a proton exchange membrane, combining with oxygen on the other side, producing water, and of course we can use that to drive something. So we end up with CO2 being produced in what's called the anode, and water produced in the cathode. We can do something similar, but we can do electrolysis. So we can feed perhaps something like acetate, which is vinegar effectively, and have something similar happening with electrons being produced. If we augment those a little with the power supply, which could be renewable energy, the protons arrive at the other side. There's no oxygen to take up the electrons. Consequently, hydrogen is produced, and that's evolved as a gas. But they can do more than that. So on the left-hand side, we have all the processes that anaerobic digestion had that I tried to intimate at least. And there's other processes happening, particularly the ones that supply electrons to the anode. But on the left-hand side, apart from the electricity we can produce, we can also produce peroxide, which is a useful bleaching agent. We can remove nitrogen from water, which otherwise also poisons our fish. We can produce acetate. We can produce all sorts of things, including glutamate, propionate, butanol. And indeed, we can go even to oils, using biology to do that. So we can create hydrogen in the way I've shown you, and that We can also produce ethanol in pretty much the way that it's produced now, but involving also electrochemical processes. And we can keep on bouncing down, increasing the number of carbons in the hydrocarbons until we end up with oils. And we know that we can produce caprate and caproate and capreate, which is 6 and 8 carbon hydrocarbons. So what do they look like? These devices are in our labs running at the moment. On the far left-hand top, you can see H-type bottle reactors. As we go along the top row, you can see some cubical reactors. They're quite small devices. And on the bottom row, you can see how we've tended to scale up in a tubular way to tubular reactors, which I'll show you again in a minute. In fact, I'll show you right now. So these are reactors sitting on the desk here. There's 4 of them. They're tubular reactors. We would have them actually linked together normally in a long line, but I'll connect them up to this little device here, and we can watch that it can drive a fan around. Unfortunately, I can't drive it fast enough to take off. We did try, but unfortunately the charging device didn't work so well. So as not to distract you, let's turn that off. There are barriers. We've been trying to make these systems relevant to the rest of the world rather than just our laboratory. So what we have to do there is improve the power performance and look at the density of bacteria on that anode, because each one has to produce some electricity. The more of them we have, the more electricity we have. We need to know what foods we can supply them and how to supply them and remove essentially their effluent from them so they don't get inhibited. How we design and configure the reactors for best performance so that we can make them bigger. And actually, the stability and robustness is also a very important fact. Probably one of the most important things is a progressive, economic and sensible approach to getting them to market. And that's quite a difficult thing because we have other technologies to compete against. So if we look at the bacteria themselves, I'm not expecting you to read that, by the way. This is a phylogenetic tree from some research we did with Surrey, in fact. You can see there's an awful lot of species of bacteria in that single reactor. And some of those, round about the middle there, a lot of the ones in the middle are electrogenic. In other words, they produce electricity. So I'd like to show you some very specific ones that have been studied in more depth, just so you can visualize them. These are from the laboratory of Derek Lovely in the States, and they're called Geobacter, and he discovered these particular bacteria, and they basically give electrons to rocks. They reduce metals in rocks as a way to get their energy. So we can use that fact to actually generate electricity. Also, we have a different one called Shawanala, named after a British microbiologist. And you can see the linkages between these. They have pili connecting each other, or nanowires as they're frequently called, and they are supposedly transferring electrons down these, and there's good evidence for that. So they're sharing energy, electrical energy between them in a cooperative way. This is some work that was done by Ian Mickey in our lab, and he looked through fluorescence microscopy and what's called fish probes to basically make certain bacteria fluoresce. And you can see that the green there is most likely non-electrogenic. In other words, they don't produce electricity, they're fermenting bacteria. And the dark black stick-like things are part of the electrode. And you can see that they're associated with it, but they're not on it. The purple, on the other hand, are more like the geobacter, and they're sitting precisely on the electrode, which indicates their function, essentially. So scaling up is a very important issue in this work, primarily because the main loss comes from resistance, internal resistance. And if you make something big, the ions have to go a long distance, and there's a lot of energy loss in doing that. So there's a geometric problem here. So what we've done is said, well, we'll fix two of the dimensions and extend the third to increase our volume, and gone for a tubular approach. It wasn't such an obvious approach at the time because we didn't know what would happen as we were changing the substrate and everything else going up the tube in a plug flow type of way. So it's clear that some sort of modularization is a good approach because you can keep things small and make them big, like the TARDIS, if you know what I mean. And we had to obviously contain liquids and keep oxygen out, and it all has to be done cost effectively. So this is quite a big headache for us. So we started off with these tubular reactors, and these are duplicates, 2 modules in each, and each module is basically a microbial fuel cell. So we were feeding sugar in one end, it was being fermented, and the next stage was doing something else. So there was different biological processes happening in the two stages. But nevertheless, we can see the sugar disappearing in the top left-hand graph there. You see it's right down at the bottom. But the power from each of the modules actually remained the same, and this was replicable. We could do it over and over again. So we did. So we doubled the size, and we doubled the size again, and we were able to double the volume and double the power. And that's essentially the holy grail in scale-up. If you make it bigger and it doesn't lose performance, then you've done what you set out to do. So we were also removing pollution potential, BOD, or chemical oxygen demand, COD. And we were doing it to a high degree. So we have a wastewater treatment process that generates electricity. If you put it in an anaerobic chamber, then all the other things that I said you could make suddenly become possible. We started looking at the materials we could use, try to optimize and reduce the losses within the system, and we've done some work with UCL in London. They supplied the very expensive and bespoke carbon, which performed very well. We got 50 watts per cubic meter out of that. But it was extortionately expensive if we tried to produce electrodes like that. So we've gone for a lower performance, but a much cheaper design, which is the bottom one. And we've done it through modeling and correlating that to experimental performance. So it's taken us to the point that now we have reactors which are performing at about 30 watts per cubic meter, which was our target, actually, for the project we're working on. We've achieved it, and we're very happy about that. And compared to an earlier version, which is the bottom white one there, which was achieving only 6 watts per cubic meter. So we've increased the power production dramatically, and we've also increased the volume. So when you imagine large volumes of wastewater coming down at you, you have to have a large volume. We've also looked at the control, the rate at which we take electricity from these poor bacteria. It's a bit like the Matrix, if you know that particular film. We extracting electrons from them, but actually it's not quite as pernicious as the Matrix, because they're getting energy out of giving us the electrons, so it's good for them. But if you keep pushing them, not so hard that you kill them, but hard enough that they feel some stress, they perform better than if you don't control them. And we managed to get 5 times as much energy out of our bacteria by controlling them than not controlling them. What's more, when we use these kind of control techniques, we could start up the process in half the time that we were doing before. And when your startup time is say, a month, then you can see that 2 weeks is quite a long time for an industrial process. Very fortuitous as well, microbial fuel cells can use the effluent from other biological processes, which is very useful. So we've looked experimentally, and indeed we've published a couple of papers on the integration of these processes with other processes so that the whole overall system becomes more efficient overall. We've looked at real wastewaters, and in this case we've looked at food wastewaters, wash-down waters from a food processing plant, curries and toad in the hole and things like that. And a company putting wastewater into the drain has to pay for that. They pay on the basis of the pollution potential. So we reduced the pollution potential by 84%, which would have been a reduction of about 50p roughly per cubic meter that they were discharging. Okay, we haven't implemented it yet, but there is potential to save money there for industry. There's a route to market perhaps. We've also looked at linking organic waste streams, like our sewage, with metal-rich waste streams, like acid mine drainage, for example. And putting them together, what we find is that we can treat them both, and what's more, we can get almost twice as much, well, more than twice as much power out of the system by virtue of using both streams. So, I'm going to sum up now. And go back to what I was talking about at the beginning. So the proposition that I was making was that to engineer is humane. And no doubt somebody, and perhaps all of you, were thinking, well, to engineer is not humane and it's not inhumane, it's just engineering and it can be used for both. And I would agree with you. However, if we believe in that overshoot and a subsequent collapse, then not engineering a soft landing, I would suggest, would be inhumane. So our systems, I'll talk about our political and our social systems and everything else depend on economic growth. And though it's not directly linked to the kind of growth I've been talking about, it does stimulate consumption and it does increase population. So I think there is a causal link. We take carbon from natural sequestered systems, oil wells and so on, and we're now re-releasing it into the environment and putting ourselves in a position where we've got a less desirable environment to live in. We've got peak oil coming in about 5 years. At the same time, we've got an increase of about 20% or more than 20% of demand, according to the IEA. I quote, warming of the climate system is unequivocal. That's the IPCC. So what can we expect? So do we expect competition for resources, metals, everything else, water, food, you name it? Do we expect competition for land? So population movement, ring any bells? Do we expect inundation? Do we expect atolls to be wiped out? I think we probably do. So I think we probably better get engineering. So it just remains for me to say some thanks. I want to thank from the bottom of my heart all of you for coming. I really appreciate the effort that a lot of you have made to get here. To start naming names would be a nightmare for me, because once I started, I wouldn't know where to stop. So what I've done is just put a whole lot of citations here, and I'm going to ask you to look at the little document that you will have received, or I hope will receive at some stage, and look at all the people I really need to thank. There's a lot of co-authors there, and what's more, there's a lot of people who aren't co-authors, but nevertheless I owe the greatest debt of thanks to as well. So I thank you all, and I thank you for listening.
thank you, Giuliano, for excellent presentation, food for thought. So I'm going to open the floor to questions. Got time for 2.
Yes. I'll take the project that you are speaking about from 2 perspectives. The first one, which is the environmental, which is fantastic. The second one is the technical, or I would say the electrical engineering side of the thing. Now, is it meant to be something for the distributed generation, or it can be embedded to the grid? And what's the difficulty if this is what you are working with?
I would suggest that at the stage they are now, it's still quite early. It's difficult to imagine them being used as generators, other than for niche applications. So you might want to generate power in remote areas, perhaps for distributed sensing or something like that. But it's unlikely that you would, say, replace a coal-burning power station with microbial fuel cells. Their real application is in treating waste, so saving energy by not doing it aerobically, which is a vast amount of energy, as much as you generate, in fact, and then simultaneously producing energy. So you can use that energy to treat the waste, so the system will run itself. So self-supporting systems is probably, at the moment, the best we can expect. However, the materials you can produce from them could add much more value to the process. Does that answer your question?
Yes, a quick question. I'm very impressed by how many people you involved in this field and how many are involved with you at the moment. In the future, it's clear we're going to need even more people doing that. What do you think of the prospect of England, Wales, Scotland, Northern Ireland, Europe producing enough engineers through their education system?
Well, I think engineering has turned around now. I think our young are much smarter than, say, my generation was. They're seeing the potential of engineering, and I think if you look at our application rate, it's gone up significantly. I remember a time where we were really skating on thin ice. So I actually have a lot of belief in the next generation. I think they're going to sort a lot of problems for us. I'm very positive about what Europeans and British can do. So I think we will be competing with China. I think we will be competing with India and Africa and all the rest of them, but they're not going to stand still. I think the problem that we've got is actually keeping up with the enthusiasm of some very motivated young people in other countries.
Thank you.
Welcome.
One more question. I think we've got time for that. The back row.
Academic researchers always struggle between scholarly activities and enterprise activities.
Yes.
As an engineering researcher, because if you are doing a scholarly activities, a lot of knowledge will be transferred, particularly the group you talk about, like developing countries and other things, they will be benefited. Whereas the things attached to IPR and other things related to enterprise activities, a lot of times the big companies hold it. End of the day, the developing countries and other things will be paying that one to achieve the benefits. What is your personal view on sort of scholarly activities and enterprise activities where we can draw a line?
I don't think we can, and I don't think we should. I think it's the responsibility of researchers, whether they're at the very fundamental end or whether they, very close to market end. It's their responsibility to actually make some capital out of the research they do. Perhaps not for themselves, but for the general good. So if we develop a wonderful process in the lab and it stays in the lab, we've just wasted our time, I think. And actually, historically, the UK has been accused of doing that too much. But again, I think things are changing. I think there's a lot more emphasis on trying to match up enterprise with research and for them to inform each other. So I don't know about you, but I receive an awful lot of emails inviting me to all sorts of speed dating kind of events for this kind of thing. It's happening, but it's difficult. So we were wanting to spin out not so long ago. We thought now's the time to do it because there's only a few companies doing it. But could we get anybody interested in funding it? No, we couldn't. Whose fault is that? Probably mine, probably ours. We haven't sold it well enough, or maybe the technology isn't up to it. Somebody else will have to decide that. But I'm personally always open. What I want to do is see the technology used. I don't see any distinction.
Okay, thank you very much, everyone. So it's my pleasure now to introduce Rob Lewis.
Where do you want me?
My name is Robert Lewis. I'm the Dean of the Faculty of Computing Engineering Science. Before I go any further, can I just remind everyone that we have lots of food waiting for us downstairs, so don't dare disappear. It all needs to be used up, and that's down in Crochets in a moment. Well, it's my pleasure to give the vote of thanks, and what struck me, Yano, when listening to the lecture was the sheer range of topics you managed to compress into 45 minutes, and I started to make a note of them. I wasn't able to keep up, but this is what I've got so far. Population growth, the predictions of the Club of Rome, water, complex mathematical modelling, program training, I think occurred somewhere, food prices, biomass, anaerobic digestion, energy consumption. It was, I think, the Victorians who noted that engineering is the art of deliberately modifying the world around us for our benefit. The fertile ground for the professionally and professorially curious, and always using the science of measurement, the probing of the engineer, and of course the calculations of the mathematician. On the subject of social unrest and food prices, I knew that my grammar school history would come in useful sooner or later, because I'm reminded of the fact that the French Revolution followed 3 very poor harvests, and so it was as much about bread and cake as it was about liberty, fraternity and equality. And then we arrived at Yano's current research, centred around organic fuel cells and electricity is produced by converting bugs into electrons, CO2 and water, so mimicking the bacterial interactions found in nature. And despite the low power density, we've seen the possible applications in the future. It is, of course, an honour to give the vote of thanks, but it's also a privilege when the speaker is so well thought of by so many people, both in his discipline and outside, and certainly across the university. I think it's true to say that many of us aspire to be as fair-minded and as considerate and also as successful in our daily work as Yano clearly is. And at the beginning of his lecture, Yano defined the meaning of the word engineer and also the word humane. And many of us recognise Yano, and here if I may paraphrase Gilbert and Sullivan, Yano as the very model of a modern humane engineer. The faculty is proud of Yano, and the university, through the conferment of this title, honours him tonight. Yano, it's my pleasure to present you with this plaque commemorating tonight's event, and I'd like to ask everyone to join with me in thanking Yano for a stimulating lecture and also to congratulate him on his achievements. Thank you very much.